Chapter 4.2 is the exponential function e to the x. So e is just a number. We call it the natural base, and it is approximately 2.718281882, and it goes on forever and ever. So e is just a mathematical constant, just like pi. And to memorize this, I recommend knowing 3 decimal places, 2.718, just like we remember pi is 3.14. You can remember e is 2.718. So there's a couple main properties here that I want us to know. The first one is that e is an irrational number, meaning the decimal goes on forever and ever and ever, and it never repeats itself. Just like pi is also irrational. And the second property is that it shows up in many applications. One example is population growth. The formula for population growth has E in it. It comes from continuously compounded interest, if you remember doing that. And for the third property, a little bit more calculus-based of a property, it is the limit as x approaches infinity of 1 plus 1 over x, all raised to the x. That limit equals e. And I believe that's one of the first definitions of e discovered. So what that means is if you take numbers getting larger and larger towards infinity, and you plug them in here and here, these x's, the larger and larger numbers you pick, the closer and closer and closer that whole expression is going to get to the number e. Okay, so those are 3 big properties for e. And now let's take a look at the actual function itself. So the function is f of x equals e to the x. So just remember that e is a number. And we know that this is going to be exponentially increasing because e is the base greater than 1. So we know it's going to be increasing. Let's pick some x values to plug in. Let's do -2, -1, 0, 1, and 2. Plug them in. And I'll just kind of skip ahead and get these decimal answers out for us. But if we plug in all those x values into e to the x, we get all these decimals. And I rounded all of these values down here to the nearest hundredth. And then from those x's and y's, we get these xy ordered pairs. So let's go ahead and plot those. First one, -2, 0.14. That's going to be something like this. -1, 0.37. 0, 1. 1 and 2.7. And then 2 and 7.39. Something like that. Connect them and we get our function f of x equals e to the f, and it's kind of is exactly like we would expect. It looks like an exponentially increasing function. So now we're going to be getting into the derivative of exponentials. So we're going to only do we're going to do 2 things right now: the derivative of 2 to the x and then b to the x in general. This is going to get expanded on and explained more in chapter 4.3. So for some things I'm just going to kind of skip, and that's because we're going to do them in the next section. So starting with the derivative of the exponential 2 to the x, if we want the derivative, so the derivative of 2 to the x, it's going to equal m times itself, m times 2 to the x. So the m here is a number. The m is the derivative of 2 to the x evaluated at x equals 0. And this is the part that we're kind of skipping over right now. This is what we're going to be expanding on in 4.3. That number is 0.693. So the derivative of 2 to the x is about 0.693 times 2 to the x. So that is the derivative. And like I just said, we're going to be doing this, we're going to be expanding on this in the next section. So for now, just know that that is the derivative of 2 to the x. Right, next thing, a little bit more general, the derivative of f of x equals b to the x. And that's going to be pretty much the same thing as we just did, except instead of a 2, we have a b. So the derivative of b to the x is going to equal m times b to the x, where m is the derivative evaluated at x equals 0. So this one, I'm just going to put a little question mark and say, okay, what the heck is that? And we'll be coming back to that once again for the 4th time in the next section. Okay, let's calculate some of these. First one, we want the derivative of 2 to the x evaluated at x equals 3. So we know from before that the derivative of 2 to the x is about 0.693 times 2 to the x. So if we're evaluating this at 3, all we have to do is plug in a 3 into x. So that's going to be 0.693 times 2 cubed, which is 0.693 times 8, which is 5.544. And I'm just going to put approximately here because we did round. That 0.693 is technically being rounded. So that's the derivative evaluated at 3. And now let's find the derivative evaluated at -1. That's going to be approximately 0.693 times 2 to the first power. And that ends up being 2 to the -1, evaluating at -1. That ends up being 0.693 times 1/2, which gives us 0.3465. Okay, so kind of taking a little shortcut and knowing the derivative without actually figuring out how we did it, and then evaluating it at a certain x value. And now that brings us to the derivative of e to the x. So one of the reasons why the exponential e to the x is so important and why we see it all the time is because the derivative of the function evaluated at 0 equals 1. And what that means is if we take the derivative of e to the x and we use the fact that d dx of b to the x equals m times b to the x, where m, in this case, is the derivative of e to the x evaluated at x equals 0, then we get this result right down here. We get 1 times e to the x equals e to the x. So that's just a very long, drawn-out way of saying the derivative of e to the x equals itself. And this portion that I wrote down over here on the right, that was just from the previous page. Okay, so kind of just the explanation in words for this is the slope of the curve y equals z to the x at any value x is equal to the y value at that point. So the slope of the function is equal to the y value of the function. The function is equal to the derivative of the function. And we can see in this graph right here, so here's the graph of y equals e to the x. If we are right here on the point 0, 1, since we're at the y coordinate of 1 and the derivative is equal, that means the slope is also equal to 1. If we are right here at the point 1, e, the slope is equal to e. And no matter where we are on the function, if we're going to have the y coordinate that's e to the x, that means the slope is also e to the x. Okay, so that's just kind of the reason why this function is so important. And for these examples, we want to write the expressions in the form a times e to the kx for some numbers a and k. Okay, so for the first one, we're going to have to use exponent rules. And that's from the previous section. So this first one here, we have 3e to the 2x squared times e to the x over e to the negative 2x. And for this one, there's a couple different ways you can actually go about it. What I'm going to do is take care of this right here first. And I'm going to do 3 squared is 9. And e to the 2x squared is e to the 4x. So what I did was I squared both of those factors separately. And that's times e to the x over e to the negative 2x. And the next thing I'm going to do is I'm going to combine these two in the numerator. Same base, we can combine them by adding the exponents. 4x plus x is 5x. And the last thing that we have to take care of is this right here. And that's going to be dividing the same bases. And that means we subtract the exponents. 5x minus negative 2x is 5x plus 2x, which is 7x. So that is 9 times e to the 7x for this example. Next one, we have the square root of e to the x over e to the 7x. And first, let's go ahead and do what's inside of the square root, the radicand. Dividing common bases, subtract the exponents. That's going to be x minus 7x, which is negative 6x. And let's rewrite the square root as an exponent of 1/2. And now we have a power to a power, so we have to multiply the exponents. Negative 6 times 1/2 is negative 3. So e to the negative 3x. So once again, these are just exponent rules from the previous section. Next example, we want to find the tangent line to the graph f of x equals e to the x when x equals 1. So every time we see the equation of a tangent line, we should be thinking, y minus y1, get that in blue, y minus y1 equals m times x minus x1. We're given x1, we actually have to find y1, and then we also have to find m. So I'm going to write this. We need x1, y1, and we need m. So we know that y1 equals f of x1. It's just the y coordinate for the x value. This is going to be f of 1. Here's the function. That's e to the first power, which is e. So our y coordinate is e, which is completely fine. You don't want that as a decimal. You just want to leave it as e. And now for m, we need to find m. M is going to be the derivative of the function, the derivative of e to the x, evaluated at the x coordinate. So the derivative of e to the x is just equal to e to the x. So the derivative of e to the x is itself. Evaluate that at x equals 1. That's e to the first power, which is also e. And if you remembered that the y coordinate is equal to the slope, then you could have just skipped that and knew that it was also e. And now let's go ahead and plug this in. That's y minus e equals e times x minus 1. And let's go ahead and simplify it a little bit. Y minus e equals ex minus e. If we add e to both sides to solve for y, the e's actually cancel, and we just get y equals e to the, or y equals e times x. So this time it's obviously not an exponential because it's a line, it's a tangent line. So it's y equals e times x. Okay, let's do a couple more examples here. Let's find the derivatives involving the expression e to the x. First one, we have 1 plus x squared times e to the x. If we want the derivative, we know that this one is going to be product rule. And let me just throw brackets around this so we know we're doing the derivative of the whole thing. So product rule says it's going to be the first times the derivative of the second. The derivative of e to the x is e to the x, plus the second times the derivative of the first. The derivative of 1 plus x squared is 0 plus 2x. Technically, that's correct. Let's factor out a GCF of e to the x and see what's left over. What's left over is a 1 plus x squared for the first term, plus 2x for the second term. And just for practice, let's keep on going. If we rewrite what's inside parentheses, that's x squared plus 2x plus 1. And I wrote it like that because now this actually factors to x plus 1 times x plus 1, which we can write as x plus 1 squared. So that is the derivative, and it's nice and cleaned up now. It looks nice and simplified. Okay, next one we have 1 plus e to the x over 2x. And for this one, it looks like this is quotient rule because we are dividing. And we want d dx of this whole expression. So quotient rule, if you remember my little phrase for it, it's going to be low d high. So the derivative of the numerator is just e to the x minus high d low. The derivative of the denominator is 2 all over low squared. So once we have that, now we have to simplify it. So simplifying this, we get 2x e to the x minus, I'm going to distribute a negative 2, minus 2 minus 2 e to the x, because it was negative and 2 here. Okay, and then this is all over. We can actually simplify that. 2x squared is equal to 4x squared. And let's factor out a 2 in the numerator. And also in the numerator, I'm just going to rewrite this as x e to the x minus e to the x minus 1. So all I did in the numerator was just flip-flopped these two spots. Just good to have the constant last. And the only reason why I factored out a 2 is because 2 and 4 cancel to 1 over 2. And we're left with x e to the x minus e to the x minus 1 over 2x squared. Good enough. It doesn't really look like it can be simplified any further, so that is our answer. All right, let's do one more here. We want the derivative of y equals e to the negative x. So a little bit different because we have a negative in the exponent now. But if we went ahead and we actually rewrote this as e to the x to the negative 1, now we can actually see that we can use the chain rule. Chain rule, or the general power rule, whatever you want to call it. General power rule is just a specific version of the chain rule. So what we're going to do is we are going to do y prime, the derivative, is going to be the derivative of the outside. So bring the exponent down, leave the inside alone, subtract 1 from the exponent, times the derivative of the inside. Derivative of e to the x is just e to the x. And we can simplify this. That's going to be negative e to the negative 2x, power to a power you multiply, times e to the x. And now we have common bases. Add the exponents. Negative 2x plus x gives us negative 1x. And that's actually our answer. Negative e raised up to the negative x is our derivative. Let me just label it again. And just for the last thing here is a little graph of y equals e to the negative x. We can write it as 1 over e to the positive x if we want for exponent rules. I personally think it's the best to know that the negative on the x means it's a reflection of y equals e to the x over the y-axis. So it's going to be an exponentially decreasing function. We know it's decreasing because 1 over e is between 0 and 1, because it's 1 divided by about 2.7, which is obviously between 0 and 1. And the other thing that we could do, we could make an xy table, pick some x values, plug them in, get the y value out, and plot them. Either way, we know it's going to look something like that function here. Okay, so that is it for 4.2.